Okay, 29.3. Now in 29.3, we're doing a very particular thing. We're taking a set of equations that we call them exact equations. EXAC, exact, yeah, equations. And we're using that form. We're getting the problem we're working in that form so we can use them. So that's the plan. So if we look at the derivative of uv, for example, that's uv prime plus vu prime, right? So if I take the integral of that, I would have the integral of the guy on the other side, right? So if I can get in that form, then I can use that. If I have something that's uv prime plus vu prime, and I'm trying to find what it is, then I can just take the integral, the derivative of uv, and come up with uv and come up with the answer. So that's the basic idea. And get to the right spot. Very good. I'm in chapter 28. 2, number 3. All right, so on page 1005, we find that the derivative of x over y, x over y is equal to y x prime minus x y prime divided by y squared, and we find that the derivative of the arctangent of y over x is equal to x dy minus y dx over x squared plus y squared. And we find that the derivative of xy is x dy y dx, which I already did. And we find that the derivative of the natural log of the square root of x squared plus y squared is equal to x dx plus y dy over x squared plus y squared. And the last guy, the derivative of x squared plus y squared to x dx plus y dy. All right, so what we're going to do is we're going to have a problem that looks like what's on the right-hand side. We're going to turn it into a problem that looks like what's on the left-hand side. Then we're going to integrate it and get the right answer. So that's the theory of the situation. And I even spelled exact right. And if it's not one of these, then we can't do it. All right. So which one do I have to do first? Number 1. So I do number 1 first. X dy plus y dx is equal to y squared dy. And okay, well that's fine, but that's not in the right form. I look over here and I see all right. Did I write it down right? Oh, yeah. Okay, that's fine. So that's going to be x dy plus. So this guy on this side is dxy. So I can write dxy is y squared dy. I can integrate both sides of the equations, and I can get xy is equal to y cubed over 3 plus c. And at that point, I'm done. That's called an implicit form. I don't have to make it any simpler than that. Okay. I could say y is equal to something, right? But that'd take me the rest of the page. So why would I bother? So implicit, M-P-L-I-C, implicit. If I have an explicit form would be y of x is equal to something. So if I could make this into y of x is equal to something where I have no y's on the other side, then that would be an explicit form. An implicit form is a perfectly okay answer. Number 6. Oh, something happened. Oh, I can't talk about it though. The audio's going. Let's stop the audio for a moment. Number 6. I have x dy minus y dx x to the 4th dx plus x squared y squared dx. Okay, well, because I'm in this chapter and I know I'm in this section, I know I'm supposed to get something that looks like what's on the other page. I'll start doing that. So I've got an x squared dx times x squared plus y squared. And then I've got an x dy minus y dx divided by x squared plus y squared is equal to x squared dx. I see that on this side I can take the integral of that quite easily. I turn the page over, and if I have an x y dy minus y dx divided by x squared plus y squared, that's the arctangent guy. So this can be substituted with the derivative of the arctangent of y over x is equal to x squared dx. Now I can solve the equation. I can integrate both sides, and I can have arctangent y over x is equal to that's an equal to sign. Didn't look like it, I know. X cubed over 3 plus c. And then, so that's good enough. We can leave it there if we wanted to. Or we could take the tangent of both sides and say y is equal to x tangent x cubed over 3 plus c. We could do that as well. But there's nothing wrong with leaving it in the form above. And as we get more difficult in math, there's no reason to try. Well, the places you're gonna make errors is 9th grade algebra. To solve a problem without using much 9th grade algebra gets you to the answer. Using more 9th grade algebra to make it simpler normally means you get the wrong answer. See how that works? So that's why we'd leave it in the implicit form. Number 10. Y plus x dx y minus x dy x squared plus y squared dx. All right, so I've got a y dx minus x dy plus x dx plus y dy is equal to dx divided by x squared plus y squared x squared plus y squared. Again, if I wasn't in this section of the book, my ability to solve what it is that I'm doing. See, this is dx here, even though I can't see it. Right. Now I'm hoping that these two forms are in the front. So I've got a y dx minus x dy over that guy, y dx minus x dy. Okay, so this is the derivative of the arctangent of x over y plus, and this guy is dx dy is the derivative of the natural log of the square root of x squared plus y squared is equal to dx. All right, so now I can integrate both sides of the equation. And I can have arc tangent x over y plus the natural log of the square root of x squared plus y squared is equal to x plus c. The integral of 1 dx would give me an x. So I got x plus, I still have a constant of integration I have to throw in. Now again, I'm not going to waste my time trying to get that into x as y is equal to something. That's going to take a miracle. Not to mention a big piece of paper. Okay, the next guy is 13. Now the interesting thing about 13 is that there's no solution to him. And the reason there's no solution to it is because they wrote the problem wrong. So the problem should read x dy minus y dx is equal to x cubed plus xy squared dy plus x squared y plus y cubed dx. And I have an initial condition that says y at 2 is 2. So I'm going to solve it and solve for the integration constant of integration. All right, well, again, because I'm in this chapter, this should be pretty duck soup. So I got x dy minus y. Now if I put a 4 here, where like the book has, then I'm hosed. I don't have any of the forms. It ain't going to work. Is equal to, we'll bring out an x squared plus y squared dy plus y x squared plus y squared dx. And I'm going to rewrite that x y minus y dx divided by x squared plus y squared is equal to x dy plus y dx. And I come back and I see that this guy is the arctangent of y over x. So this is derivative arctangent y over x is equal to, and this guy is the derivative of what? Of xy. Alright, so now I integrate both sides of the equation. Get the arc tangent of y over x is equal to xy plus c. Alright. So that used to be okay, and we could stop there, but now we have an initial condition, and it says that y at 2 is 2. Okay, so the arc tangent of 2 over 2 is equal to 2 times 2 plus c. Now, what's the arctangent of 1? Arctangent of 1. 45 degrees, right? Tangent of 45 degrees is 1. Arctangent of 1 is 45 degrees. So this would be pi over 4 is equal to 4 plus c, which implies very strongly that c is going to be equal to pi over 4 minus 4. So now we can write a final answer, and it would be the arctangent of y over x is equal to xy minus 4 plus pi over 4. Yeah, that's what that says. Okay, and we could check our work. We could have the arctangent of 2 over 2 is equal to 2 times 2 minus 4 plus pi over 4. And we come to the same conclusion, pi over 4 is equal to pi over 4, and our work checks. Okay, so much with that. Do you want more, or is that enough of that section?
Not for me.
Okay, we'll move on then.
Well,
Alright.
we can get caught up
Now-
a little bit.
Oh, that's never an issue. 20. The final exam will have the same stuff on it, whether we cover it or not. This is a particular cool way to solve a differential equation, and is what you use for probably 1/3 of the equations that you come across in physics and in the electronics world. So this, if I have an RL circuit or an LC circuit, no, an LR circuit or an RL circuit, I would use this method to do it. So RC, RL, so a capacitor and resistor, or an inductor and a resistor in my circuit, I would use this formula. And it says that if I have something in the form AX Y prime plus BX Y is equal to CX, then I would go and change the formula. I'd divide by AX and have BX over AX Y is equal to CX over AX. And then I'd change it so that this would be Y prime is equal to plus PX Y is equal to QX. So what I would do is, if I had something in front of the Y prime, I would divide everything by it and get into that form. Once I have it in that form, and P of X and Q of X are functions in X only. So P of X can't have any Y's in it, Q of X can't have any Y's in it. They're functions of X only. Functions of X only. They could be 1, they could be 2, they could be a whole number, right?
Yeah.
So f of X is equal to 1. That'd be a function of X, even though there's no X's on the right-hand side of that equation. It'll still be okay. If I can do that, then I can go e to the integral of px dx. We call this our integrating factor. We also call it our fudge factor. So we could call it either one of those things. So if I was going to be formal, I'd call it my integrating factor. If I was going to be less formal, I'd call it the fudge factor. All right. Then, once I have that, I'm going to say that y is equal to 1 over the e to the integral of px dx. Integral qx e to the integral of px dx. So I'm going to solve this guy separately, and then I'm going to put him there, I'm going to put him here, and then solve that integral, and that's going to be the answer to my problem. Okay? Good enough? Now, there's a proof there showing you how that is possible to do. And this particular line is not there. On page 1008, it keeps that, the integrating factor, on the other side of the equation, which is pretty silly because you don't want it on the other side of the equation. All right. So I got a sine wave here, sine omega t, and I got 10, I got a 40, I got a 50, I got an 80 ohm resistor, and I've got an inductor that's 1 Henry. Okay, what's the voltage across the resistor? Voltage is equal to IR. What's the voltage across the capacitor? Voltage, not the capacitor, inductor. Change in I, change in D, L. So that means that di, and L is 1. So di dt plus IR, which is 80, is equal to sine omega t. Okay, this is in the form I prime plus 80I is equal to sine omega t. My P of X is in t only. My Q of X is in t only time. I want e to the integral 80 dt. E to the 80t. Okay, so I is going to equal, my current's going to equal 1 over e to the 80t integral e to the 80t sine omega t dt. Now all I have to do is solve that integral and everything would be fine. I'm pretty sure that interval's in the back of my book. If it's not, it's with the extra ones. Alright, so enough of doing a hard thing. We want to do number 10. So I've got x, y prime, plus 2y is equal to x squared plus 4 cubed. Okay, so I got the problem written down, right? I'm not in the right form. Huh? What? That's not number 10?
dy dx is y prime.
Yeah, that's y prime. Yeah, dy dx is y prime. Yeah, no problem there. All right, now I'm not in the right form, so I'm going to get myself to the right form. Y prime plus 2 over xy is equal to x cubed plus x cubed, x squared plus 4 cubed over x. Okay, so this is my p of x, and this guy over here is my q of x, and I want to find on the side e to the integral 2 over x dx. So I want to find that guy. So e to the 2 integral 1 over x dx. That's e to the natural log, 2 natural log of x, which is e to the natural log of x squared, which is x squared. Okay, so now I'm going to go and say y is equal to 1 over x squared integral x squared plus 4 cubed over x times x squared dx. 1 over x squared integral x squared plus 4 cubed x, because I got an x squared on top and an x on the bottom. Okay, so I'm going to guess that my answer is in the form x squared plus 4 to the 4th. I'm going to take the derivative of that, and I'm going to get 4 x squared plus 4 cubed times 2x. So I need an 8 here, and I need a 1 over 8 on the outside. Okay, so if I do that, I can have y is equal to 1 over 8 x squared times x squared plus 4 to the 4th plus c, like that. And I could call that done if I wanted to. Okay, good enough? 10. Next problem is 22. Okay, 22. dy dx minus y over x, x squared plus 3, and I have an initial condition y at 1 is 3 that I'll apply later. Okay, so I'm in the right form. P of x is equal to minus 1 over x, and q of x is x squared plus 3. So I want to find e to the integral minus 1 over x dx. Okay, so I got e minus the integral 1 over x dx, e minus natural log x e natural log 1 over x. 1 over x. Alright, now that I know that, I know that y is equal to 1 over x integral x squared plus 3 times 1 over x. Alright, so I got y is equal to x integral x plus 3 over x dx. X times x squared over 2 plus natural log of x cubed plus c. So that'd be 3 natural log x, but that's the same as natural log of x cubed. So. Alright, so I end up with x cubed over 3 plus x natural log x cubed plus cx is y. Okay, I'm applying my initial condition, which says y at 1 is 3. Okay, so I'm going to have 1 in there for the x. 1 half plus the natural log of 1 is 0 plus c, implying that c had better be 2 halves. Okay, so final answer, y of x is x cubed over 2 plus x natural log x cubed plus, we'll make it 5 halves x. Okay, good enough? Well, I guess we can, it's an even problem, right? It's not in the back of the book, so we won't look. Okay, good. Don't have to look. Number 30. Oh, you gotta be kidding me. Gotta be kidding. Y prime, y sine x is sine x. And y at 90 degrees is 3. Okay, so I see that my p of x is sine x, and my q of x is sine x. I want e to the integral sine x dx. So that's going to be e to the minus cosine x. Integral, the derivative of sine is cosine, but the integral of sine would be minus cosine. Okay, so now I've got y is going to be equal to 1 over e to the minus cosine x integral sine x e to the minus cosine x dx. Well, let's see. I guess I'll guess. I'm going to guess my answer is e to the minus cosine x. Y prime is going to be e to the minus cosine x times the derivative of minus cosine, which is sine x. My guess is correct. Okay, so my final answer, well, not my final answer, I still have initial condition 1. Well, we won't do that. We'll just call it e to the cosine x times e to the minus cosine x plus c. Okay, so y is equal to 1 plus c e to the cosine x. Applying the initial condition, y at pi over 2 is equal to 3. Okay, so y at pi over 2 is equal to 1 plus c. Pi over 2 is 90 degrees, cosine of 90 degrees is 0, e of 0 is 1, blah, 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 implying c is equal to 2. So final answer, y is equal to 1 plus 2 e to the cosine x. Okay, now we're going to go into Maple and see if Maple thinks that's the right answer. Right? Because I'm doing the even ones on purpose so that you can't look in the back of the book to see if I'm right. It only seems fair that we go and look to see if something's right sometime today, right? Just any time today? All right, so ordinary differential equation solver. Okay, so we're going to add an equation. We want y's, and we want x's, and we want a first order guy, and we want a zero order guy, and we want a plus sign in between them, plus sign, and we want this guy times sine x equals sine x. All right, do I have that right? I might. The derivative is equal to that times sine x is equal to sine. That looks good. Now the initial condition, y at pi over 2, oh bummer, how am I going to get pi over 2 over there?
Could you type in 90 degrees?
No, it's got to be in radians. Might be pi over 2 is equal to 3. Can't be that easy though. Come on. Oh yes! Oh yes. Error. The value for the initial condition must be algebraic. It is algebraic. Alright, so we're done. Oh, it's calling pi a parameter. Shit. Okay, well, we'll go back and delete the initial condition and solve it without an initial condition, and then we'll use that to get the initial condition. Alright, so that's 1 plus cosine blah 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 blah. So I get the same thing, and c is still going to have to be 2. Okay, so I get the same answer, but I can't. The differential equation solver is not letting me put in pi.
Instead of pi, could you just type in 3.14?
Yeah, but then that would be, I could. Let's see if I can go. Can I go back? Back.
It wouldn't be exactly pi, but it'd be close.
Well, let's say at 4 is 2. Why doesn't it like that? Y at 4 is 2. All right, then we're going to solve it. But what we're going to do is show the commands. All right, and then we're going to go and take these commands and we're going to copy them. And then we're going to paste them up here in Maple. Paste them in Maple, and then we're going to say pi, and then we're going to change this. So it's supposed to be equal to 3. So we're going to change this to 3, and we're going to change this to pi over 2, and now I have pi right there. Pi divided by 2. Okay, get rid of the 4. Parentheses. Okay, now it ought to like it. Ta-da! Alright. So we can take Maple and bend it to our will. Alright, so y of x is 1 plus 2 e equals x. Alright, did that guy. Okay, so now we should do 29.5, and then we'll be halfway caught up. Alright. Okay, so 29.5 is story problems. Excellent, just what we always loved, story problems. And 5, 6, 7. And notice that 5, 6, 7, and 8 all have the same thing in common. Resistors, capacitors, voltages, things like that. Okay, so we're not doing the ones that aren't electronic, which is the sole purpose of having a Tech Math 4 class, to solve electronic problems. Yeah, exactly. So we have in series, we have a resistor at 80, and we have an inductor at 0.1 Henry, and we have a voltage supply that looks like a battery at 120 volts. And I at 0 is 2 amps. Okay, now there's no switch or anything in the circuit, right? So that's why we have that initial condition. This circuit is going to have current running in it until there's no change in current. Then this guy is a short, and at that point we're going to have 120 over 8, which is 3 halves of an amp flowing in the circuit from there on. So that we know what the circuit's doing, okay? Because a DC circuit, the inductor is going to be a short, but it's going to be a short after 5 time constants of R over L. So our time constant is 800 seconds. Or is it? No, it's L over R. So our time constant is L over R. So that'd be 0.1 divided by 80, which is whatever that is. But that's not relevant to our analysis of the situation. All right, so back to the issue. The voltage across the resistor is IR. And the voltage across the inductor is DI dt L. So using voltage drops, we have 120 volts has to equal 80 I plus 1/10 I prime. Okay, clearly we're not in the right form, so I'm going to multiply everything by 10. di I prime plus 800 I is equal to 1200. P of x is 800. Q of x is 1200. Couldn't anything be nicer than that? E to the integral of 800, and we can't change it dt. We'll change the variable to time. E to the 800t. I is equal to 1 over e to the 800t integral 1200 e to the 800t dt. I is equal to e to the minus 800t times. Okay, so I needed 800. All right, so this is going to be 1200 divided by 800 e to the 800t plus c. I is equal to, that's 3 over 2, right? 3 over 2 plus c e to the minus 800t. And when I at 0 is 2, I at 0 is 2? I at 0 is 2, which is 3 over 2 plus c and that's a 1, implying that c is 1/2. So final answer, I of t is equal to 3/2 e plus, where's my plus sign? Plus 1/2 e to the minus 800 t. And as t gets bigger, after 3 half-lives, this is going to be extremely small. I'm going to get the 3 halves that I told you that after 5 time constants. So now the issue is, what is the time constant? Is the time constant 800? It is. I forget. Yeah, whatever it is. So that's my final answer. Number 6. I have a capacitor. I have charge. Blah, 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 blah. I have a capacitor with initial charge. Okay. So I know nothing. So I know that the only thing I know is that that equation is correct. And I is dq dt. So I have r q prime plus q over c is equal to 0. I can divide by r to get in the right form. Is equal to q over rc, which is equal to 0. And I know that q at 0 is equal to 3. Okay, so what do I have? I have a resistor and I have a capacitor with some Q0 on it. I have no voltage. I shut it out and the capacitor discharges. After 5 time constants, it'll be totally discharged. My time constant is RC. Okay, those are the things I know. But from a mathematically point of view, P of x is RC and Q of x is equal to 0. And I want e to the integral RC dt, which is going to be e to the RCT. And then I'm going to say I is equal to 1 over e to the RCT integral 0 times e to the RCT dt. I get I is equal to e to the minus RCT. That's sort of like minus the time constant RC times some constant. Integral of 0 is going to be 0, but I'm still going to have a constant left over. I'm going to have I at 0. Oh, shit. How did I get I? I'm supposed to have Q's everywhere. Where did I mess up and turn it to I? So this is a Q is equal to, this is a Q is equal to, this is a Q. So Q at 0 is 3 coulombs, implying that C is equal to 3. And my final equation, Y, no, it's not a Y. Y of T, the charge, 3e to the minus RCT. So if I told you the initial charge on the capacitor was 3 coulombs and the time constant was RC, you could tell me without any help from the equations that would be the case. Okay, looking at 7. I'm done looking at 7. Anybody want to do it for me? I was hoping. Number 7. so I got a resistor, and I have an inductor, and I have a voltage source. And the voltage source is 10 sine 2t. And the resistor is 4 ohms, and the inductor is 1 Henry, and the voltage across the resistor is IR, which is the same as 4I. Is 4I, and the voltage across the inductor is I prime L, and L is 1. Okay, so I can write that I prime plus 4I is equal to 10 sine 2t. Sine 2t. Alright, so my P of x is 4, and my Q of x is 10 sine 2t. I want e to the integral of 4 dt, and I'm going to add e to the 4t. Okay, so I is equal to 1 over e to the 4t integral 10 sine 2t e to the 4t dt. Oh, gee, isn't that nice? Anybody remember what that integral is? I didn't think so. Neither do I. But I have it on good authority, and it's in the back of the book. Looks like it's number 59 on page 1169. So number 59, page 1169. All right, so I of t is going to equal e to the minus 4t times. We'll bring the 10 out because I don't need it on the inside. 10 out. And that's going to be e to the at, okay, so that e to the 4t times 4 sine 2t minus 2 cosine 2t divided by a squared. 4 squared is 16 plus n2 squared, which is 4, plus some constant c. Okay. So I got a 20 sitting there. I got a 20 sitting there. I got a 10 over here. I of t equals 1/2. That guy's going to go away. 1/2 4 sine 2t minus 2 cosine 2t plus 10 c e to the minus 4t. But it's not 10. There's no 10 there. Because I already took the 20 and put it over here, and I got a 1/2. That's our 1/2 sitting there. Okay, final answer. I of t equals 2 sine 2t minus cosine 2t plus c over 2 e to the minus 4t. Do we have an initial condition? This is number 7?
Yep.
Okay, I at 0 is 0. Go on, so I at 0. So that makes this not my final answer. Okay, so I of 0, which is equal to 0. This guy's 0 minus 1 plus c over 2. This guy's 1 has to be 0. implying C is equal to 2. And now it's time for my final answer. Final answer, I of t is equal to 2 sine 2t minus cosine 2t plus e to the minus 4t. And this is odd, so we can look it up in the back of the book. The thing about a differential equation is you can't tell whether or not it's right until you've checked it. So this is section 24.5, number who? Number 7. And you'll believe me when I tell you it's right? So check with back of book. Okay. Check with back of book. And that's how an electrical engineer would solve that problem. And what's the current at time t? And because you're a algebra-based class, we never did that. Well, I did that a couple times for you already, probably. Dr. Hewitt may have done that for you too, just for the heck of it, just because he knows he can. All right, number 8, and then we'll go home. I won't go home. I still have a differential equation class at 3 o'clock. Find the equation of the circuit of the current I. Okay, so I've got a resistor, 300 ohms. I have an inductor. You can tell the difference between the inductor, right, and the resistor in my drawing very easily. And I have a voltage of 120 volts. Be nice to know which side was positive, wouldn't it? Initial condition, I at 0 is 0. Okay, so the voltage across the resistor, 300I. The voltage across the inductor, 1/10 I prime. So I got 1/10 I prime equals 300 plus. Plus 300I is equal to 120. Multiply everything by 10. I prime plus 3,000. 1,200. That's my P of x. That's my Q of x. I want e to the integral px dx. E to the integral 3,000. I'm changing my variable to t. E to the 3,000 t. I at t equals 1 divided by e to the 3,000 t, integral 1200 e to the 3,000 t dt. E to the minus 3,000 t. All right, now that integral is going to be e to the 3,000 t over 3,000. That's what it's going to be. Does 12 go into 30? No, it doesn't. Power. Okay, so I'll write this as 12,000 over so that's 12,000 times e to the 3,000 t over 3,000 plus c. Yeah, that'd be like that. and I take the derivative of this and I get that. That looks good. Alright, so I'm going to have I of t equals, he goes away, 12 over 30 plus 12,000 c e to the minus 3,000 t. Okay, that looks good. I at 0 is 0. Is that true? Yes, that's true. Which is 12 over 30 plus 1200 c, implying c is 1 over 3,000. Okay. That's pretty weird. No, it's not. Minus. That's better. Minus 1 over 3,000 because I have to equal 0, right? Alright, so final answer. I of t equals 12 over 30 minus 12 over 30 e to the minus 3,000 t. So at the very beginning, my current is nothing. I start, my current's going to be nothing because I have a big change in current that's going to stop the voltage as time goes on. I'm going to have current flowing, and then this is going to be a short, and then I'm not going to have any change in current, and then I'm going to have current flowing continuously. And the continuous current will be 12 over 30. Where the heck did it go? 12 over 30 amps. I didn't want to do that. Undo. Okay. Okay, questions? All right. Control, Alt,